somewhere in a warehouse right now, a piece of furniture is being designed around a box, not around strength, not around load, but around what fits cheapest inside a shipping container. And that decision is why your bookshelf wobbles, your drawers peel apart, and your bed frame strips itself the second time you move it. This is the story of how shipping economics quietly became structural engineering, and why particle board and MDF are standing in for something they were never built to replace. This video is brought to you by the Durability Project, where we explore why the things we buy no longer last, and the engineering decisions that quietly shape their lifespan. Cut open the edge of a flat pack panel and look at what is actually there. Not the wood grain surface film, not the painted face, the cross section. What you see is gray, uniform, and faintly dusty. Chips and shavings and sawdust, the leftover material from real lumber operations, compressed under heat and pressure and locked together with urea formaldehyde resin. That is particle board, not wood, the industrial residue of wood pressed into a shape that wood used to occupy. For most of the 20th century, a chest of drawers was built from solid oak or walnut planks, with continuous grain running through every piece. That grain was doing real structural work. Cellulose fibers running along their length transfer force the way a bone does, distributing load across the whole structure rather than concentrating it at a single point. The furniture was heavy, expensive to move, and built to outlast the person who bought it. A dresser from 1930 is still a dresser today because the material it was made from was chosen for how it performs under load, not how it fits in a shipping container. Then mass retail met global logistics, and solid lumber lost the argument. It is inconsistent from board to board, expensive to mill, and dense enough that shipping costs eat into margins fast. It does not stack flat, so manufacturers moved to particle board and MDF, medium density fiberboard, materials that can be produced in perfectly uniform sheets, cut to any dimension and stacked by the thousands in a single container. The cost per unit dropped sharply. The structural properties dropped with it. At the fiber level, the difference between solid wood and particle board is not a matter of degree. In solid wood, cellulose fibers run in long continuous chains, oriented along the grain, and that orientation is what gives the material its tensile strength. In particle board, those fibers are broken, randomized, and rebonded with adhesive. The resin fills the space between particles, but it cannot replicate the fiber continuity that made the original wood strong. So you get a material with decent compressive strength. It holds up under a steady vertical load, but very poor tensile and shear strength, which is exactly what every furniture joint experiences under real use. In simple terms, real wood bends and shares the load. Particle board cracks and concentrates it. The numbers make the gap concrete. Solid oak has a modulus of rupture, a measure of bending strength, around 14,000 pounds per square inch. Standard particle board sits between 1,600 and 2,400 pounds per square inch, depending on grade. That is 6 to 8 times weaker, not in theory, but in the exact way furniture fails in your home. MDF is slightly better behaved. Its finer, more uniform fiber structure gives it a smoother surface and more consistent density across the sheet, but it shares the same core vulnerability. Both materials are held together by adhesive chemistry, not fiber continuity, and that adhesive has one enemy that exists in every home on Earth: moisture, not flooding. Just the ambient humidity of a bathroom, a basement, a kitchen. Urea formaldehyde resin is hydrophilic. It pulls water in at the molecular level. The resin swells. The particles push against each other. The surface delaminates. A particle board shelf rated for 40 pounds in a dry room can lose its structural integrity within months in a humid one. Not all at once, but steadily, and without any way to reverse it. The material holds its shape under ideal conditions: dry, static, undisturbed. But the hardware holding it all together introduces a second failure mechanism, one that does not even need moisture to get started. Open the hardware bag from any flat pack kit and lay the pieces out on the floor. What you have is a handful of cam lock fasteners, small metal discs roughly the size of a coin, a few wooden dowels, some L brackets, and a single Allen wrench. That is the entire structural system holding together a piece of furniture that might weigh 80 pounds and carry several hundred more. The cam lock is not a bad piece of hardware for what it was originally designed to do. In light-duty applications, holding together thin panels under low, steady loads, it works fine. But furniture is not a light-duty application. A bookshelf full of books, a bed frame under 2 adults, a dresser being dragged across hardwood during a move. Those are dynamic load conditions. They generate shear forces, racking forces, and impact loads. The camlock was never designed to resist any of that. A camlock doesn't fail all at once. It fails one assembly at a time. The mortise and tenon joint has been the standard connection in solid wood furniture for roughly 3,000 years, and the reason it lasted that long is purely mechanical. A tenon, a projecting tongue cut from one piece of wood, fits into a mortise, a matching cavity cut into another. Load transfers through direct physical contact between wood surfaces, across a contact area measured in square inches. Under racking force, the tenon bears against the walls of the mortise and holds. It does not strip, it does not pull out. Glue it, and it becomes even stronger. But even dry, it holds, because the geometry itself is doing the work. This is not a design oversight. It is a direct consequence of designing furniture around a flat box. The joint has to be fully assembled by a person with no tools and no training after delivery, which means it cannot be a mortise and tenon, because a mortise and tenon arrives already assembled. So the structural load gets transferred to hardware, and the hardware gets threaded into the weakest material in the panel. When a bookshelf racks, when lateral force pushes the top sideways relative to the base, the camlock bolt goes into tension and the disc goes into shear against the wall of its drilled hole. The particle board around that hole is the weakest point in the entire load path. It crushes, the hole elongates, the joint loosens, and a loosened camlock joint does not recover because the material it was gripping has already permanently deformed. Wooden dowels take a different path to the same end. The dowel bond fatigues under repeated dynamic load. A drawer opened and closed thousands of times. A chair rocked back on 2 legs. The dowel works loose. The joint develops play. That play becomes impact load. The impact load accelerates the fatigue. The joint isn't designed to last, it's designed to survive the return window. A mortise and tenon in solid oak resists racking loads measured in hundreds of pounds and holds for generations. A camlock in particle board begins losing its grip the moment a single adult sits down nearby. 12 million tons of furniture hits American landfills every year. Not because people are careless, because the material itself was never meant to last. It was meant to ship cheaply, assemble once, and hold together just long enough. Particle board soaked through with humidity cannot be dried back to strength. A camlock hole crushed out by racking load cannot be tightened back down. The failure is not a defect you can return. It is the endpoint the system was designed to reach. The oak dresser from 1910 is still holding because it was built around load, not logistics. The furniture in your living room was built around a box, and boxes don't care how long anything lasts. Brought to you by the Durability Project.